Imagine a major fintech platform processing millions of transactions. One night, a network glitch triggers a partial failure during a high-value fund transfer. Because the team blindly implemented a choreography-based Saga pattern without understanding compensation logic, the system entered a zombie state. Money was deducted from the sender, but never arrived at the receiver, and the compensating transaction failed due to an unhandled edge case in the ledger service. For 12 hours, the data was inconsistent, leading to a $10 million reconciliation nightmare and a complete loss of customer trust. This is the brutal reality of distributed systems. When you move away from the safety of a single database, you aren't just changing your code, you are changing the physics of your data. Many architects treat MSA patterns like a fashion trend, but in a distributed environment. A single misunderstood pattern can become a ticking time bomb for your entire enterprise. But what exactly makes these systems so much more dangerous than the monoliths we used to build? We will uncover the structural flaws that lead to such catastrophes by the end of this lecture. In the traditional monolithic world, we relied on ACD properties. When you hit save, the database guaranteed that either everything happened or nothing happened. It was simple, reliable, and handled by the database engine itself. However, in microservices, we move toward the base model. Basically available soft state and eventual consistency. We trade immediate consistency for scalability and availability. But this trade-off comes with a heavy price. You no longer have a global lock. You are now responsible for managing state across multiple network hops, where network partitions are a mathematical certainty, not a possibility. This shift requires a fundamental change in how we think about truth in our data. If you try to force ACID behavior into a distributed MSA using two-phase commits, you will likely destroy your system's performance and availability. This tension between scale and consistency is where most projects fail. Does this mean MSA is inherently flawed? No, but it means your survival depends on mastering specific patterns. But wait, if these patterns are so complex, is there a map to guide us through this chaos? To navigate this landscape, I have categorized the 12 essential MSA patterns into 4 critical pillars: communication, data, reliability, and observability. We will explore everything from the API gateway and service mesh to Saga and CQRS. But we aren't stopping at traditional MSA. We are entering a new era where AI agents are becoming the primary orchestrators of these services. Interestingly, the way an LM agent plans a multi-step task is structurally identical to how a Saga orchestrator manages a distributed transaction. By understanding these 12 patterns, you aren't just learning how to build better backends. You are learning the architectural foundation for the next generation of AI-driven enterprise systems. This crossover is where the highest-paid architects currently operate. We will look at how an AI agent can use a sidecar to interact with legacy systems and how observability patterns are the only way to debug an agent's reasoning path. But how do we know which pattern to pick for a specific problem? Let's look at our analytical framework. My goal for this course is to give you more than just a list of definitions. Any AI can give you a definition. I am here to provide the when not to use criteria, the scars from 25 years in the field. This is the level of depth required to pass professional engineering exams and to lead high-stakes technical interviews. For every pattern, we will analyze its force multiplier effect and its technical depth cost. You will learn to recognize architecture anti-patterns before they sink your project. By the end of this journey, you will have a decision-making framework that allows you to choose the right tool for the right scale. Remember, the best architects aren't the ones who know every pattern. They are the ones who know which ones to avoid. We are starting at the very edge of your system. If the entry point fails, nothing else matters. In the next chapter, we dive into the entry and edge patterns, the API gateway, and the complexities of service-to-service communication. Are you ready to see why your current gateway might be your biggest bottleneck? In a distributed environment, letting clients talk directly to dozens of microservices is an architectural suicide mission. This is where the API gateway pattern steps in as a single entry point, handling cross-cutting concerns like authentication, rate limiting, and protocol translation. However, as we move towards multi-device ecosystems, a single gateway becomes a bottleneck. This led to the evolution of the backend for front-end or BFF pattern. Instead of one generic gateway, we create specialized edge services for mobile web and third-party integrations. This decoupling allows front-end teams to iterate independently without being held back by a monolithic edge layer. Think of it as a concierge service tailored for specific guest types, ensuring that the payload is optimized for the target device's bandwidth and processing power. But here is the critical question. In a dynamic cloud where IP addresses are ephemeral, how does the gateway actually find the target service? The answer lies in a mechanism that works like a real-time GPS for your architecture. Modern infrastructure is volatile. Instances spin up and down based on traffic, meaning static IP configurations are a relic of the past. To solve this, we implement the service discovery pattern using a service registry like Netflix Eureka or HashiCorp Console. When a service starts, it registers its network location with a registry. The gateway then queries this registry to discover where to route the traffic. This isn't just about finding an address. It's the foundation for intelligent load balancing. Using client-side load balancing techniques, the gateway can distribute traffic based on the health and capacity of individual instances. If a service instance fails to send a heartbeat, it's automatically evicted from the registry to prevent traffic black holes. This dynamic lookup process is what allows your system to scale from 10 to 1,000 instances without manual intervention. But wait, if every single request must pass through this one gateway, aren't we just creating a massive, centralized point of failure that could sink the whole ship? Architects often fall into the fat gateway trap, where they keep adding business logic into the entry point until it becomes a distributed monolith. From my field experience, this is the #1 reason MSA projects fail during the second year of operation. When you put domain logic in the gateway, you increase latency and create a single point of failure or spiof. If the gateway goes down, your entire ecosystem is dead. Furthermore, as the gateway grows, it becomes a deployment bottleneck. Every team has to wait for gateway updates to release their services. You should avoid a centralized gateway when your latency requirements are sub-millisecond, or when your organization consists of highly autonomous teams that shouldn't be coupled by a shared infrastructure layer. For those massive scale environments, we need a way to handle networking logic without centralizing it. Is there a way to decentralize these edge functions? Indeed, and it starts with a concept called the sidecar. To solve the centralization problem, we use the sidecar pattern. Imagine a motorcycle with a sidecar. The motorcycle handles the core logic, your business code, while the sidecar handles the extra tasks like logging, monitoring, and network security. In the world of Kubernetes, this means running a separate container alongside your application container in the same pod. This allows developers to focus purely on business logic in any language: Java, Go, Python, while the sidecar handles the infrastructure glue consistently across the entire organization. We also see the ambassador pattern here, which acts as a specialized sidecar for outgoing requests, abstracting away complex retree logic and circuit breaking. It's a clean separation of concerns that brings sanity to a chaotic network. But as the number of services grows from 10 to hundreds, managing these individual sidecars becomes a configuration nightmare. This leads us to the most hyped, yet most misunderstood, architecture in modern history. Enter the service mesh. If the sidecar is the component, the service mesh is the entire management system. Tools like Istio or Linker divide the world into two halves: the data plane and the control plane. The data plane consists of all those sidecar proxies intercepting every bit of traffic between services. The control plane acts as the brain, pushing configuration, security policies, and MTLS certificates to those proxies. This gives you invisible features like automatic mutual TLS encryption, fine-grained traffic shifting for canary deployments, and deep observability without touching a single line of application code. In a tech-heavy organization, this is the holy grail of reliability. However, here's the cold reality check. I've seen teams spend more time fighting their service mesh configuration than actually building features for their customers. The complexity, astronomical. How do you know if you are actually ready for this, or if you're just chasing a trend that will kill your delivery timeline? Before you adopt a service mesh, you must pass the maturity test. If you haven't mastered basic CI/CD, centralized logging, and container orchestration, a service mesh will only accelerate your failure. It introduces significant network latency. Each request now has multiple extra hops through proxies. It also demands a dedicated SRE team just to maintain the control plane. Use this checklist. Do you have more than 20 services? Do you have strict compliance requirements for internal encryption? Do you need sophisticated traffic routing that standard Kubernetes ingress can't handle? If you answer no to these, stick to a simple API gateway. We've covered how requests enter and travel through the system, but we haven't touched the hardest part of MSA. Once the traffic arrives, how do we manage data consistency across different databases without a global transaction? That's the distributed transaction nightmare, and we're diving into the Saga and CQRS patterns in the next chapter to solve it. In the monolithic world, we relied on ACID properties and two-phase commit to ensure data integrity. But in a distributed microservices environment, 2PC is a performance killer and a scaling nightmare. This is where the Saga pattern enters. Choreography-based Saga is the decentralized approach where services communicate through events without a central coordinator. When an order-created event is fired, the payment service listens and acts. It's elegant and highly decoupled, making it perfect for simple workflows. However, the biggest risk here is cyclic dependencies and the blind spot. As the number of services grows, it becomes nearly impossible to track the global state of a single business transaction. You might find yourself in a distributed spaghetti situation where debugging a failed order feels like chasing a ghost across 10 different message queues. But what if we need a central brain to manage this chaos? Question: does adding a controller violate the core principles of microservices, or is it a necessary evil for complex logic? To solve the visibility issues of choreography, we use orchestration-based Saga. Here, a central orchestrator or state machine tells each service what to do and when. It's much easier to implement complex conditional logic and monitor the current status of a transaction. Interestingly, this architectural pattern is exactly what we see in modern AI agent frameworks. Just as an AI agent orchestrates various LM tools to complete a multi-step task, a Saga orchestrator manages microservices to complete a business goal. However, beware of the God service anti-pattern. If you put too much business logic into the orchestrator, you've just built a distributed monolith. The orchestrator should handle sequencing, not domain logic. If your orchestrator starts looking like a 5,000-line script, you are doing it wrong. Payoff. Now that we have a brain, we need to talk about what happens when things inevitably break the art of the undo. In a distributed system, you cannot roll back a database transaction that has already been committed by another service. Instead, we use compensating transactions. The third step in a 5-step Saga fails, you must execute the undo operations for steps 1 and 2 in reverse order. This is a semantic rollback. For example, if you can't refund a credit card, you might issue a store credit instead. This adds significant complexity to your codebase as every do operation must have a corresponding undo operation. Failure to handle semantic rollbacks correctly leads to data inconsistency that requires manual intervention, the ultimate nightmare for any SRE. You must also consider pivot transactions, the point of no return. Once the pivot transaction commits, the Saga must go forward to completion. Teaser, but how do we guarantee that the event to trigger this undo is even sent if the database crash happens exactly at the wrong moment? The dual write problem is the silent killer of MSA. If you update your database and then try to send a message to Kafka, what happens if the network fails between those two actions? You get a ghost update. To solve this, you must use the transactional outbox pattern. Instead of sending the message directly, you save the message into a special outbox table within the same database transaction as your business logic. A separate message relayer process then pulls this table and publishes it to the broker. This ensures at least once delivery and atomic consistency between your state and your events. Without this, your Saga will eventually drift into a state of eventual corruption. Enterprise architects often overlook this until they see thousands of inconsistent records in production. Question, but once we have all these events flying around, how do we query them efficiently for the UI? In traditional systems, we use the same model for both reading and writing data, but as traffic scales, the complex joins required for the UI start to throttle your update performance. Command query responsibility segregation, or CQRS, suggests we split these into two. The command side handles the domain logic and state changes, while the query side is optimized purely for fast data retrieval. Think of it like a specialized dashboard via a secure vault. By separating them, you can scale your read database independently from your write database. You could even use different technologies, PostgreSQL for writes and Elasticsearch for lightning fast reads. Question, this sounds perfect, doesn't it? But is the cost of maintaining two separate data models always worth the performance gain? If CQRS is about how we access data, event sourcing is about how we store it. Instead of saving only the current snapshot of an object, we store every single change that has ever happened as a sequence of events. To get the current state, you simply replay these events from the beginning. This gives you a perfect, immutable audit log. It's like having a time machine for your data. If a bug is discovered, you can time travel back to the exact moment of failure and reconstruct the state to see what went wrong. For highly regulated industries like fintech or healthcare, this isn't just a pattern, it's often a legal requirement. Teaser, however, replaying 1 million events every time you want to see an account balance is clearly inefficient. How do we handle that? Now, for the hard truth, CQRS and event sourcing are high-octane patterns that will destroy a simple project. If you are building a standard CRUD application with low traffic, the added complexity of managing eventual consistency and read lag will slow your team down significantly. This is the eventual consistency trap. A user updates their profile, hits refresh, but still sees the old data because the read model hasn't synced yet. You have to design the UI to handle this, perhaps by using optimistic updates or read your own writes consistency. If your domain isn't complex enough to justify the overhead, avoid this pattern at all costs. Payoff, this brings us to the most practical part of CQRS, how to actually build those fast read models without going insane. To bridge the gap between the event store and the user, we use projections to create materialized views. A projection service subscribes to the event stream and updates a read-optimized database in real time. This is where you pre-calculate everything. If your UI needs a list of top 10 customers with total spend, don't calculate that on the fly. Have a projection service update a specific table every time a purchase completed event occurs. This shifts the computational cost from the read time to the write time. This is the secret to building high-performance systems like Netflix or Amazon. Bridge, we've covered how to manage data, but what happens when the network between these services fails or a service becomes unresponsive? In the next chapter, we'll dive into resilience and observability patterns, the safety nets of MSA. In a monolithic world, a single failure might crash the process, but in a microservices environment, failures are contagious. When a downstream service becomes slow or unresponsive, upstream services wait for timeouts, eventually exhausting their own thread pools. This is the domino effect. The circuit breaker pattern is our primary defense. It operates in 3 states: closed, where traffic flows normally while monitoring error rates; open, where the circuit trips after a threshold is met, immediately returning an error to save resources; and half open, probationary state to test if the downstream service has recovered. From a professional engineer's perspective, failing fast is always superior to hanging indefinitely. However, remember that a circuit breaker is not a cure-all. If your timeout settings are poorly configured, the breaker might never trip or trip too often, causing unnecessary downtime. Have you considered what happens when the circuit stays open for too long? it can lead to a complete system blackout, which brings us to how we isolate these failures using architectural boundaries. Even with a circuit breaker, one malfunctioning endpoint can consume all available threads in a service, effectively starving other healthy endpoints. This is why we use the bulkhead pattern, named after the partitions in a ship's hull. If one compartment is breached, the others remain buoyant. In software, this means isolating resources like thread pools or connection pools for different services or criticalities. For instance, your payment calls shouldn't be blocked because the recommendation service is hogging all the threads. In enterprise architecture, we often implement this using separate thread pools for each external dependency. But be careful, over-partitioning can lead to resource fragmentation where threads sit idle in one pool while another is starved. It is a delicate balancing act of resource management that requires deep knowledge of your traffic patterns. But wait, even with isolated resources, what if the failure is just a transient network glitch? In those cases, we don't want to give up immediately. We want to try again, but with caution. The retry pattern is the simplest way to handle transient errors, but it is also the most dangerous if implemented blindly. If you retreat a non-idempotent operation like a charge credit card request with a unique transaction ID, you risk double charging the customer. This is a classic silent killer in financial microservices. To implement this safely, you must pair retries with an idempotency key, typically a UID generated by the client. The server stores this key and, if it sees it again, returns the previous result instead of processing the transaction twice. Additionally, always use exponential backoff with jitter to prevent the thundering herd problem, where all retrying clients hit the server at the exact same moment. In the field, we see many developers omit jitter, leading to synchronized spikes that crash recovered servers. This brings up a critical question. How do we even know which service failed if the request passed through 10 different layers? The answer lies in how we observe the system. In a distributed system, a single user click can trigger a dozen microservices. If an error occurs, checking logs on one machine is useless. We need log aggregation and distributed tracing. Log aggregation centralizes logs from all containers into a searchable store like Elasticsearch. However, logs alone aren't enough to reconstruct the sequence of events. That's where distributed tracing comes in. By injecting a unique trace ID into the header of every request, we can follow the breadcrumbs through the API gateway, auth service, order service, and database. Tools like Jaeger or Zipkin visualize these spans, showing us exactly where the latency spike or error originated. Without this, debugging a production issue in MSA is like searching for a needle in a haystack while the haystack is on fire. But even if we can trace the past, how do we know if a service is healthy right now? This leads us to the distinction between just being on and being ready. Kubernetes and modern orchestrators rely on health check APIs to manage the lifecycle of your services. However, a common anti-pattern is confusing liveness with readiness. A liveness probe tells the orchestrator if the process is alive. If it fails, the container is killed and restarted. A readiness probe, however, tells the orchestrator if the service is actually ready to handle traffic. For example, a service might be alive but still loading a massive cache or waiting for a database connection. If you only use a liveness probe, your service might get stuck in a crash loop backoff because it was killed while it was simply booting up. Conversely, if a service is healthy but the database is down, the readiness probe should fail so the load balancer stops sending traffic it cannot process. This subtle difference is what separates stable production environments from chaotic ones. But once the service is healthy, how do we manage its settings without rebuilding the entire image? This is where dynamic configuration enters the picture. Hard-coding configuration, or baking it into Docker images, is the ultimate anti-pattern in MSA. Environment variables are better, but they become unmanageable across hundreds of instances. The solution is externalized configuration. Using a config server or tools like HashiCorp Vault, we can decouple the application code from its settings. This allows us to update feature flags, database credentials, or timeout values in real time without restarting services. It also ensures a single source of truth across dev, staging, and production environments. In professional practice, we use dynamic refresh to allow services to pick up new configurations on the fly. This level of agility is what makes MSA powerful, yet it introduces complexity that must be carefully governed. As we conclude this chapter on resilience, think about this. If these patterns can make microservices resilient, how can they be applied to the next frontier of tech? In the next chapter, we will see how these exact same concepts are evolving to manage the unpredictable behavior of AI multi-agents. In current architectural shifts, we are seeing a fascinating convergence. The orchestration of AI multi-agents is becoming structurally identical to microservices architecture. When you build an agentic workflow, you are essentially deploying a set of distributed, autonomous units that communicate via messages to achieve a complex goal. However, unlike traditional microservices where an input A usually yields a predictable output B, AI agents introduce non-deterministic output. This means your architecture must handle variance as a first-class citizen. From a professional engineer's perspective, an AI agent is simply a microservice with an LLM-based reasoning engine at its core. If you treat them as monolithic black boxes, you lose the observability and scalability required for enterprise-grade AI. We must apply MSA principles like loose coupling and service discovery to these agents to prevent a chaotic spaghetti of LLM calls. This shift requires us to rethink how we define service boundaries when the logic inside is no longer hard-coded but probabilistic. But what happens when one agent in this chain hallucinates or fails its specific task? This is where a classic MSA transaction pattern becomes a lifesaver. When a multi-agent system executes a complex task such as a research agent gathering data, followed by a writer agent generating a report, the risk of hallucination acts exactly like a technical failure in a distributed transaction. If the writer agent detects that the research agent's data is inconsistent, we cannot simply roll back a database in the traditional sense. Instead, we apply the Saga pattern. We treat the correction process as a compensating transaction. If the verification step fails, the system triggers a self-correction loop where the prompt is refined and the previous step is re-executed with new constraints. This is a stateful orchestration where each agent's output is verified against a set of business rules or another critic agent. In the field, we call this an agentic Saga. By using the Saga pattern, we transform a fragile chain of LLM calls into a resilient, self-healing workflow that can recover from the inherent unreliability of generative AI. This ensures that the final output meets the strict consistency requirements of an enterprise system. But how do we actually track these complex reasoning steps for future auditing and model improvement? It turns out we need a way to store the thoughts of our agents. In a sophisticated AI system, the thought process of an agent is often more valuable than the final answer. To capture this, we implement event sourcing for AI. Instead of just saving the final string in a database, we store every thought, action, and observation, the react pattern, as a sequence of immutable events. This provides a complete audit trail of the agent's reasoning chain. Why is this critical? Because when an agent fails in production, you need to replay the event stream to understand exactly where the logic diverged. Moreover, this event log becomes the gold mine for future fine-tuning. You extract successful reasoning chains to create better specialized models. We use an asynchronous inference model here, the agent and inference a started event, and the system reacts when the inference completed event arrives. This prevents your entire system from blocking while waiting for a slow LLM response. By decoupling the reasoning state from the application state, we gain the ability to debug non-deterministic behaviors that would be impossible to trace in a standard CRD-based architecture. However, exposing these agents directly to the internet is a recipe for disaster. Prompt injection and runaway costs are real threats. As you scale to dozens of agents using multiple LLMs like GPT-4, Claude, or Llama 3, you cannot manage them individually. You need an AI gateway. This is an evolution of the traditional API gateway, specifically designed for LLM governance. The AI Gate handles prompt governance, filtering for prompt injection attacks, and masking PA, personally identifiable information, before it leaves your network. It also manages token quotas and rate limiting at a granular level, preventing a single runaway agent from burning your entire monthly budget in minutes. Furthermore, it provides LLM load balancing and fallbacks. If OpenAI is down, the gateway can automatically route the request to an Azure-hosted instance or a local Llama model. This layer of abstraction is what separates a prototype from an enterprise-ready AI platform. It allows architects to enforce security and cost policies without touching the agent's core logic. We have now seen how MSA patterns like Saga, event sourcing, and gateways are the foundation of modern AI. But let's be honest, does every project actually need this level of complexity? In the final chapter, we will strip away the hype and give the final architect's verdict on when to embrace MSA and when to run away. After navigating through the complexities of Saga, CQRS, and API gateways, we need a way to make sense of this architectural chaos. Looking at the landscape of 12 patterns, the ultimate decision always boils down to two X's: data consistency, complexity, and service coupling. On this 2x2 master matrix, we see that patterns like distributed transactions or synchronous orchestration sit in the high-risk quadrant of tight coupling. Conversely, the event-driven Saga pattern offers low coupling, but demands immense management of eventual consistency. Real-world experience shows that architects often fail because they choose a high-consistency pattern for a low-impact domain, leading to unnecessary latency. For instance, in a high-frequency trading system, CQRS is mandatory to separate read-heavy loads, but in a simple CMS, it is pure technical debt. You must evaluate the cost of compensation logic before committing to an asynchronous Saga. If your business cannot tolerate a 5-second delay in data reflection, do not use it. This matrix serves as your primary filter for architectural governance. But even with the right map, how do you defend these choices in a high-stakes technical interview or a professional certification exam? To wrap up this journey, we must look at these patterns through the lens of a professional engineer. In certification exams and high-level architectural reviews, you aren't just asked what a pattern is, but when not to use it. Keywords like idempotency, compensation transactions, and write-ahead logs are the DNA of a robust, distributed system. However, the most critical lesson from the field is this: no pattern is sometimes the best pattern. If your team is small or your domain is still evolving, a well-structured modular monolith is far superior to a poorly implemented MSA. We call this architecture right-sizing. Blindly following patterns leads to resume-driven development, where the system complexity exceeds the business value. Whether you are designing for AI agents or a legacy migration, remember that every pattern carries a hidden tax in the form of observability and deployment overhead. Use the Saga pattern when you have a truly distributed long-running process, but keep it simple with synchronous calls until you hit a physical scaling limit. This concludes our guide. You now possess the tools to not just build microservices, but to protect your project from the very patterns intended to save it. Does your current project truly need all 12 patterns? I'll leave you with that question to audit your next sprints.